Well, alrighty, shall we begin? Excellent. Great. Well, welcome everybody to AMS Weatherband's last webinar of the 2025 AMS Weatherband Jamposium. This is Light in Air, Understanding and Appreciating Atmospheric Optics with Dr. Lourdes Aviles, Beth Katz, and Ryan Knapp. Dr. Aviles will also be our moderator for this session. Now, before we begin today, for last time, I would like to address some of the guidelines for our webinar. If you have any questions during the course of the webinar, please put them in the YouTube chat. It should be found on the right side of your viewing screen on YouTube. We have dedicated some time for audience questions after the presentation, but as always, if questions arise during the flow of the presentation that are relevant to the topic being discussed, they may be addressed at that time. Additionally, all communications should be appropriate for a professional audience that includes individuals from diverse backgrounds. So please be inclusive and respectful in your interactions. And now I'd like to introduce today's moderator. Today's moderator is Lourdes. She is an AMS fellow and a weatherband maestro who has written articles about rainbows, ice halos, auroras or northern lights, and snowflakes. She has been fascinated by atmospheric optics since she was a little girl, asking her parents what rainbows are and why the sky is blue. Before becoming associate provost, she was a professor of meteorology for nearly 20 years, both at Plymouth State. She holds a BS and MS degrees in physics from the University of Puerto Rico and a PhD in atmospheric sciences from the University of Illinois at Urbana-Champaign. I think I said that all correctly. She authored an AMS published book about the Great New England Hurricane of 1938 and is currently working on an AGU, or American Geophysical Union, textbook about atmospheric optics. She lives in New Hampshire with her family and enjoys choral singing and nature photography. Lourdes, I hand it over to you now. Thank you.
Thank you so much, Gideon. Welcome, everybody. And I am extremely thankful to the Weatherband members who chose this topic as one of the ones they wanted to see highlighted at Jamposium. And I believe that last year's attendees also were involved in choosing the topic. Today we have, there's a lot of important things happening in the world, and there were a lot of important topics covered, but this last session is about something that the three of us might be a little biased, thinking is extremely fascinating, and it gives us the joy of weather, the atmosphere, of meteorology, in a way that we can all be excited about it without having to worry about the bad weather. So as Gideon said, I'm one of the panelists slash presenters as well. So we're going to get me out of the way by starting with my presentation. I will introduce our other speakers, Ryan Knapp and Beth Katz, in more detail once I'm done with my presentation, and I will read their bios right before their specific presentation. So let me share my screen here and start my part of it. And let's see, right here. Oh. All right, all three of us are going to share the theme of light in air. And I'm going to focus on the science and cultural aspects of atmospheric optics. Beth is going to focus on the wonders of looking up, and Ryan on photography of atmospheric optics. So here we go. So many things can be seen in the sky. Rainbows, ice halos of many different kinds, shadows, even the blue skies and the red sunsets and the auroras. Some of it are very simple to explain. Others are really, really complicated. And you might imagine that people that were attuned to looking at the sky were surprised, mesmerized, fascinated, fascinated, sometimes even scared by what they were seeing in the sky, and formed uh, explanations of what they were seeing, and eventually started to wanting to scientifically understand what they were seeing. I have spent the last several years working on this textbook that Gideon mentioned about the science and history/culture of atmospheric optics for the American Geophysical Union. So stay tuned for a couple more years, I think. Don't tell them. But and also, as he mentioned, I have written some articles. I have the honor of being one of the maestros for Weatherband, and I have the exciting opportunity to send articles every once in a while in topics that I think will be interesting to people. Ice halos was one, rainbows and little known aspects of rainbows was another one. Then snowflakes and how they're six-sided and how to make paper snowflakes. The picture on the bottom right was actually taken by one of our the two pictures by one of our panelists today. And the last one that I submitted was about auroras, the northern lights. And the articles are getting longer and longer. I promise I will reverse that trend in the near future. So what I want to do is speak of the ingredients of atmospheric optics and a little bit of how that works. Give an example of rainbows and halos because they have the easiest science to explain, and also some examples of how these topics have worked in culture or are expressed in popular culture. And I could really talk about this for about 10 hours. So I apologize that today we will only be able to do some highlights. And I volunteer myself for doing a longer webinar about any of these topics or maybe the overall topic. I like to think of atmospheric optics as needing a recipe. You cannot have the atmospheric optics if one of these three ingredients is missing. Some of them are really obvious. Others we don't think about too much. But first we need the electromagnetic radiation, the light coming from the sun. We need the atmosphere because if not, most of the optics that we see, we wouldn't be able to see if there was not an atmosphere. I'll talk more about that in a second. And the one that would seem the most obvious is that we need our eyes and we need our brains to interpret what we are seeing. That would seem really obvious, but it actually has more nuance than you would think. If I talk about that first ingredient, the vision, we don't have a lot of time to go into it, and it falls a little bit outside of our scope. But on the left is a cross-section of the human eye, and then an enlarged little bit of the retina in the back. And we have these cells that the simplest way in which they work is that they absorb light. And on the right, you can see a graph that shows a blue line, a green line, and a red line, because we have three types of sensors. These are the cones that detect color. And they each have a range of wavelengths that they can detect. And between the three of them, and with complicated pathways and ways in which the brain organizes the information, that makes us be able to see the spectrum of colors that we think of as the rainbow, the colors of the rainbows, which is at the bottom right there. And after I talk about light, I'll show you an example that shows how this is relevant. Sunlight, obviously, without the light of the sun, we wouldn't be here in the first place. But that is the main ingredient, the one that will be what allows us to see the optics. All stars produce electromagnetic radiation, and that includes not just visible light, but things like ultraviolet, infrared, and depending on the star, you can have other wavelengths, shorter and longer. We all know from our days in elementary school that light can be separated, specifically white light, and sunlight is, for all purposes, white light. can be separated into the spectrum of colors that we think of as the color of the rainbow. Relevant to some of the optical effects is the fact that each of the colors have different wavelengths, with the reds and oranges having the longer wavelengths, and with the blues and violets having the shortest wavelengths. And we'll talk about how that matters just a little bit. And this light that comes to us from the sun is the one that interacts with the atmosphere and everything that's sitting in the atmosphere. Here's an interesting example. The graph at the bottom is a simplified depiction of the wavelengths of solar radiation that we get. So you can see that there's a peak of solar radiation that corresponds to visible light. And then most of the sunlight that is not visible light is UV or infrared. So mostly visible light, a little bit of UV, a little bit of infrared. And by the way, the reason we call visible light is because that is what our eyes can detect with those cells that absorb light. So it's kind of a self-fulfilling definition. So here's at the top, there's an example that was posted on what was then called Twitter. The middle is a regular rainbow that we would see. Then this person took a picture also with a film or a camera that was and that could detect infrared and that could detect ultraviolet. So if we use this gap in the trees as a reference, you see the rainbow is right here, right to the right of the gap. The ultraviolet is right on the gap, so it's under the violet. And the infrared is further to the right. So it is above the red. So infrared is above the red and ultraviolet is under the violet. So the amazing thing to think of is the fact that the rainbow doesn't end with the red on top, it continues. And if our eyes could detect infrared, we would see more. And the rainbow doesn't end with the violet at the bottom. If we could see ultraviolet, we would see more. And some animals, if they could understand what a rainbow is, they actually can see in those ranges. So if we could see what they see, their rainbows would be different, for example. But then there's the atmosphere. All light that we see that comes from the sun has been affected by the atmosphere. And the atmosphere has many things in it. And obviously, the atmospheric gases are there. And those matter because the molecules of gas matter. They interact with light. You can have aerosol solid particles that can also interact with light. But the big boy is water. We have tiny water droplets in fog and clouds, larger droplets that precipitate like drizzle, and the largest in rain. We also have ice crystals. All of these can affect light in many different ways. So on the left is a very simple summary of what can happen to light as it moves through a medium. You can think of it as a transparent medium or between two transparent mediums. So it can be transmitted without being affected. It can be what we learn in middle school. It can be reflected. It can be refracted, or a combination. Other things like it can be absorbed partially or fully. It can be bent, which we know as diffraction, or it can be simply scattered. And there's an interplay between the size of the particles in the atmosphere and what happens to them. What if you can have reflection or scattering or any other combination. Some of the effects are wavelength dependent, and I'll show you in a second. So here we go. If we think from smallest to largest, the smallest are the air molecules. they scatter visible light, and that is wavelength dependent. And no time for that now. That can be a Maestro article write-up or a separate presentation. But that's what gives us blue skies and red sunsets. They're also involved in the emissions in auroras. Then as you get a little bigger with dust particles, and you can have a lot more scattering, that all the colors are scattered, so you see white. So whitish scouts, hazy skies, with cloud and fog droplets, those are a little bigger, and that effect is a lot stronger. So you see white. That's why clouds, you think of them as white. Same with fog. They also can create some interesting interference effects that, again, we're not going to talk about them today, but coronas and glories and things like that. Drizzle can also cause some of those interfering effects. Sometimes you see that rainbow continues in an interference pattern, and others related. And then the big ones, rainbows, that are from reflection and refraction in associated with raindrops, and ice halos of many different kinds, where you have reflection and refraction associated with ice crystals. So, and it is truly, and you can explain that very easily, the reflection and refraction, with very simple middle school science. But there's an overarching mathematical description that is pretty complicated and not necessary for most purposes, but you can get all these effects from that treatment. It's called me theory. So here's my little science examples that use reflection and refraction. Let's start with the left, with the rainbow, right? The rainbows are on the opposite side of the sun. So for you to see them, you need light reflected toward you. And that reflection happens inside the raindrops. So these are the raindrops falling, and light gets refracted and then reflected, but different colors are refracted differently. So it starts separating into the colors. When they get back to you, they're separated, but you see colors coming from different drops. And I went into detail in the Maestro article about that. For halos, ice halos, it's also reflection and refraction. For most of them, it's refraction. So halos are on the simple halos, the 22-degree halos that I'm showing here, are on the same side of the sun. And the ice crystals, we have different shapes, possible shapes of ice crystals, all with six-sided symmetry. But the ones that are good for halo formation are the columns and the plates that can serve as little prisms. So when you have randomly oriented column-shaped ice crystals, the light of the sun comes to you through the center, but it also comes to you as after being refracted inside the prisms and toward your eye, and you end up seeing a circle around the sun. But ice halos are many. There's many, many different kinds, and I'll highlight some of you in a moment. So you can imagine you're in the ancient times minding your business, and suddenly this gigantic thing that looks like an eye shows up in the sky. That cannot be a good sign, right? So throughout history, ice halos have been seen as omens in the sky. Good omens, bad omens. Eventually, farmers started noticing that you could do a little bit of weather prediction. When there was a halo in the sky, they normally happen in the cirrus clouds, ice clouds, very far north of a warm front. So if a warm front was coming your way, you might see a halo, an ice halo in the sky a day or day and a half or two before the steady precipitation from a warm front gets your way. So throughout history, they have been seen And, there can be spots and lines and circles and arcs of different kinds in different parts of the sky, depending on the shape of the crystals and the height of the sun and all sorts of details. You can find write-ups where, I don't know, explorers will see a cross in the sky. And to them, that's a sign from God that they're doing the right thing. You can see all sorts of these marks. Here's a complex halo display that, many different types of crystals at many heights and many combinations of refraction and reflection. You can see all these together much more rarely. But you can also see them individually. You can see the 22-degree halo, the sundogs, the circumzenithal arc. They all have names, and I find it very fun to learn all the names and identify them. Looking back, this one always caught my attention, even though I haven't seen it somewhere else, like Old Testament, a prophet, Ezekiel. He spoke of a wheel within a wheel with rims full of eyes. And people say that's an UFO. I say it's a halo. If you say this is an artistic depiction of what that could be, but look at this. Here's a wheel within a wheel. It's very hard to see, but this is a 46-degree halo. That's the wheel within a wheel. And all those patches can be eyes. So I'm saying Ezekiel saw a halo, a complex halo display. Here's one from the birthday of the king. February 28, 1647-48. That has to do with the fact that Julian calendar and Gregorian calendar had different starts in the year. And here we go. They saw a circumzenithal arc. They're talking about 3 suns. Well, it's the real sun and then 2 sundogs. So that's what they saw. Not that the sun split in 3 to celebrate the king's birthday. And then if we move to rainbows, rainbows have captured the imagination of humankind from the beginning of time. Mythology, trying to explain what the rainbows were. Religion uses them. Cultural movements use them in many ways, and I'll highlight a few of those. On the right here is one of the most famous stories, right? The Noah, the biblical story of Noah and the flood. And at the end, a rainbow came out to show the promise that that would never happen again. So used to show promise. This is a depiction of the goddess of the rainbow, Iris. I found that in a collection of the New York Public Library. And sometimes she's depicted using the rainbow as a bow, like here. But she's also spoken about using the rainbow as a bridge between the world of gods and the world of men, or to move, because she was a messenger between the gods and men. And speaking of bridge, the Norse mythology used rainbows as a bridge also between the world of gods and the world of men. And the famous Bifrost was this bridge, rainbow bridge, and it's more commonly known these days from the Marvel universe as, connecting Asgard with Earth, and, Thor and his siblings and friends ride their horses on it. Political parties have used rainbows for a long time. Every time you have a coalition of smaller parties that come together out of convenience to try to gain a majority against a bigger threat. And more recently, LGBTQ combined identity uses the rainbow flag. I didn't put it here, but the Rainbow Bridge has been used also much more recently as a metaphor for where the dead pets cross into a meadow where they wait for their owners. And we didn't talk about Northern Lights, very complicated topic. And again, I wrote a very long article about it for the maestros. But even though a very small percentage of the world population would have been exposed to them, because this is at very high latitudes where there were a lot less uh, inhabitants, they also wanted to explain it. Spirits of the dead, the souls of those unborn, fighting dragons, people playing with a walrus skull, walruses playing with a human skull, all sorts of wonderful explanations about why you were seeing those lights in the sky. So, wrapping up my part here, the science of atmospheric optics is all encompassing. It goes all the way from astrophysics and quantum mechanics and chemistry and anatomy and physiology. It can be really complicated. Some things can be very simple. And humans have been fascinated by it for many, many years. First, trying to understand it with the tools they had available, that being mythology or religion, or with the science they had available. That's becoming more and more sophisticated. And we by no means understand everything now, but we know a lot more. Um, I invite you to send me optics pictures if you wish to do that. And I might use them or not, depending on my write-ups or my book. I put a website resource there, atoptics.org.uk. That's an oldie but goodie. It's a reference to all atmospheric optics enthusiasts. It went away for a little bit, but it has come back as a .org. On the right is a rare picture of me taking pictures of atmospheric optics during a fun event that I mentioned in one of my articles. And that is it for me. And before I stop sharing, I want to highlight a little more my co-speakers today. Continuing the theme of light in the sky, Beth is going to talk about looking up, as I mentioned. Beth Katz is a retired computer science professor, adjunct faculty at Millersville. And her and I started interacting in atmospheric optics groups and on Facebook, sharing pictures. We have a lot of common interests when looking at the sky. So we shared pictures and interactions, and we actually have never met in person, but I very much thought of her as a person that could contribute to us here. And I will read her bio in a second. Ryan Knapp is a senior meteorologist at the famed Mount Washington Observatory that has an amazing vantage point to see all sorts of different types of atmospheric optics. A lot of times it's covered in the clouds, but that means that sometimes you can see cloud optical effects. And when it's clear and the northern lights are there, it's the best place in New Hampshire to see the northern lights. And Ryan, it caught my attention, not just for being the observer and meteorologist at Mount Washington, but his amazing photography, which is why I thought that he was perfect to do one of the presentations today. So I am gonna stop my share and introduce to you our next speaker. Drink some water after I'm done, because now I'm thirsty. Beth Katz has been interested in meteorology since tracking Hurricane Celia as it approached her home in August 1970. But she got distracted by computers, earning a BS in computer science and English from the College of William and Mary, and an MS in computer science from the University of Maryland, College Park, where she was ABD for her PhD. ABD means all but dissertation. She spent her professional life teaching computer science at Furman University for 4 years, and then at Millersville University of Pennsylvania for over 20 years as an adjunct faculty member. That position let her raise her kids, explore nature, including weather and astronomy, and become involved with scouting. Throughout her life, she has been looking up, taking pictures, and explaining the sky to others. Welcome, Beth. I think you might be muted.
Okay, you can hear me, and my talk is over here, and let's start it. Hopefully that does the right thing. There we go. Share. That it?
Yes.
Looks good, Beth.
Okay. So, welcome to the I like to think this is the dessert of the whole symposium, and that we're doing the fluffy part where we don't have we're not predicting things, and we don't have mission critical anything. But I want to encourage everyone to look up. Um, Remember what inspired you to become a meteorologist and a weather person, and enjoy the cool things that we have outside. And that's what I do with scouting, with my kids, with everything, is get out there and have a good time. And so this is crepuscular rays in Denver, Colorado. And it was just, after a storm, it was beautiful. Okay. So why do we look up? We want to enjoy beautifully cool things. There's so many cool things up in the sky. I want to inspire others to learn more. You can just enjoy it the way it is, or you can say, hey, what's the science behind this? And so that's what part of what Lourdes was doing. Remember when you were little and you started looking up, or something caught your eye? You were encouraged somewhere along the way. And so encouraging the next generation of meteorologists, I think that matters. Or just scientists. Not everybody's going to do this professionally. Like I said, like she said, I was considering becoming a meteorologist, but then I got distracted by computers and doing cool stuff with that. So I did that. Maybe looking up helps you understand the weather implications. A lot of times when you have the hazy sky for um, like right now, I have hazy sky outside, mostly sunshine. Maybe that means that the weather's going to be changing a little bit. And so I'll mention that a little bit later. Foster curiosity, and remember the wonder that inspired you. But mostly just go outside and see what's out there. I labeled all my pictures, all of the pictures except one I took. And that one has a label on it. And so like here, I have a picture of a corona I was blocking the sun, a circumzenithal arc, and a 22-degree halo, and a cloud shadow, which could be like a puzzle about something. When should you look up? Well, sunrise and sunset are really easy. Rainbow conditions, I'll talk about those. The right kind of clouds, having like wispy cirrus clouds, or the high thin cirrostratus, and sometimes the bumpy thin cirrocumulus are good things that you can have. The light goes through them and gets refracted, and so it does cool stuff. Look before the fronts, and some of the cool things are when you have a big tropical system pushing in. Sometimes you get really nice, interesting looking halos just that are unusual. I remember seeing something, I think, with maybe with Hurricane Sandy coming in, and you're like, oh, why do I have halos now? Oh, because there's something big coming in. Something Lourdes didn't mention, she had a picture of it in there briefly. Flying in airplanes. Sit near the windows. Really matters. And so you can I'll mention that in one of my slides also. And also you can look at nighttime at the moon. This picture has a circumzenithal arc up at the top. Oh, I'm not sure if I can do there up here. A halo, an upper tangent arc. There may be a peri arc here, and the sundogs over on the side. Okay, where to look up? I mentioned airplanes. So airplanes, this is not the sun. This is a subsun. The sun's up here, and this is below the sun. and there were sundogs on either side. It was really cool. You can also, if you're on the other side of the plane, so that you have like the shadow of the airplane, you could see it over on the, you can see the shadow of the plane and have a glory around it. You may have a sun pillar over the setting sun. That's something to look for. Opposite the sun. So like you're saying, oh, well, I'm going to be looking oh, this is a really cool sunset. Well, look on the other side, opposite part of the sky. You might see the belt of Venus, and which is the rising Earth shadow. Look around the sun or the moon. At the same level of the sun, I'll show you some of those things. High overhead, and I guess this was a sun pillar over the setting sun, and this was an earlier, like in January, but I saw one last night. Okay, you can also look like below the sun if you're at a really high altitude. You might, or high elevation, you might be able to see something lower. Okay. Looking up safely. Okay, so we all went through having the solar eclipse and that we shouldn't look at the sun. So you shouldn't look at the sun, block the sun. I so often walk out the door, hold up my hand and say, okay, block the sun. Okay, is there anything around the sun? That's what I was doing here with the corona picture over here. I just held up my hand, stretched it out. Sometimes you can block the sun with some architecture. But if you're using your camera, a lot of times you can just take a picture and you may get an internal reflection inside the camera, but you don't have to block the sun. It does help sometimes though, because then you can not have it just like overpowering the camera sensor. Let's see, that was a Corona 22-degree halo. And then this was a really cool parhelic circle, which goes all the way around around the horizon at the same level as the sun. Sundogs, these guys here. A 22-degree halo. There's an upper tangent arc, and I think there's probably a periarc up there too. And so rainbow conditions. What do you need to do to have a rainbow? Okay, you need bright sunshine. You need raindrops. The rain needs to be opposite the sun, and the sun needs to be low enough. Okay, if the sun is high in the sky, if the sun is high in the sky, the rainbow is going to be really, really low, because the inner arc of the rainbow is 40 degrees above your head, or wherever you're taking whatever the camera. And so this is 40 degrees. And so if the sun is too high in the sky, the rainbow is going to be down here in the grass. And so you need to be looking, that's why you get like morning rainbows or evening rainbows. I have, however, seen rainbows at noon, but that was when it was in winter. It was a January rainbow, and the sun was low enough, even at noon, to be able to do that. Some of my notes here have like, you stretch out your hand. I don't know if this is how this is going to look on the camera. If you stretch out your hand, your fist at the end is 10 degrees. And so you can measure from your head, above your head, and stack that up 40 degrees. That's where the rainbow should be. And that's this part about it. Extended fist width is 10 degrees. Okay, and this is a double rainbow with wheel features. The 22-degree halo, and you say, oh, 22 degrees. Let's see, that's 2 fist widths away from the sun. You need to have thin clouds. It's often only partial. You just see little bits and pieces. And that's where you're going to have just like a circle around the sun. And these happen a lot, an awful lot of the time. You just notice, oh, hey, there's, the cast of the sky is a little bit hazy. Hey, is there a halo? Sundogs in the parhelic circle. Sundogs are either side of the sun, 22 degrees out, and they're going to be at the same level as the sun, and that's what Lourdes had for the king picture there. So this is over here is a sundog. Over here on the lower left is something called the 120-degree parhelion. It's another kind of sundog, but it's on the parhelic circle that goes all the way around the sky at the same level as the sun. And these do not occur very often. But I've managed to see a lot of them because I'm always looking up. And I was really surprised that, oh, hey, I've seen these more than you would really think that they would happen. You might see a circumzenithal arc. It's high above the sun, and it's like a smile in the sky. It's one of those fun words that Lourdes was talking about. Circum means around, and zenith is straight overhead, and so your circumzenithal arc is not all the way around the zenith, but it's would be if you drew the whole circle. And so they are very, very cool, very often very, very bright, could be very transitory. I see them sometimes in condensation trails from jets, just because on a very clear day that works. And then circumhorizontal arc, you say, well, circum horizontal, okay, so it's going to go around, and it goes all the way around the sky, but it would be below this, and it's below the sun. These, the sun has to be high enough in the sky. Right now, at the end of February, I'm at 40 degrees north, and I think I can't see a circumhorizontal arc until maybe the sun will not be high enough at midday until like mid-March. And there's some parts of the world you're not going to be able to see it at all because the sun doesn't get high enough. Okay, the belt of Venus. This is opposite the sun when at sunrise and sunset. The dark part down here is the rising or setting Earth shadow. And you have like, this is sort of like the sunset or sunrise colors, and the Earth shadow is below it. Points to remember. I think this is my next to last slide. We each see our own rainbow. The rainbow is being created by individual raindrops and the sunlight going through each of those individual raindrops. So the rainbow that I see is not quite the same rainbow the person standing next to me sees. They're often very transient, but widespread. My favorite thing like right now with the Parade of Planets is don't hype it. Just enjoy it. It doesn't have to be, oh, wow, a double rainbow. It doesn't mean anything. Okay, culturally it may mean something, but it doesn't mean that the world's ending or it's fantastic or anything. There are a lot of fun words and languages, and circumzenithal, a sundog is dogging the sun. This dark band in between the primary rainbow and the secondary rainbow, this is Alexander's dark band. There's things are named after people, whatever. You never know what bit of the adventure, the thing you're seeing is going to capture somebody's attention, trigger their enthusiasm, and spark their interest in what's going on in the world around us, and looking up. This is the one picture that it's from somebody else, is a friend of mine. We were at a hotel on either side of a wall, and he was facing one way and I was facing the other, and he saw the rainbow and I didn't. But he took a picture. It was early morning sunrise and it was really cool. Okay. So, and this is the sun pillar that I saw last night. And I was on my way to a training. I was like, oh, isn't that a cool thing? And isn't that cool sun? And ooh, wait a minute. The conditions look like there was a lot of glow over there. And so I stopped my car at an appropriate place and took a picture through the window. It had faded by the time I could really stop and get out and get a better picture. But I just keep looking up, and I would encourage you to keep looking up. Feel free to contact me, ask questions, whatever, and things. So hopefully I didn't start my timer, so I'm not sure how long I went. Sorry.
No worries. Thank you, Beth. That was wonderful. I'm gonna move to present to you our next presenter, and if there's time after we're all done, we'll answer any questions that come through. I haven't received any yet, but here we go. Originally from the Lake Tahoe region of California, Ryan was born into the alpine lifestyle. He began his Mount Washington Observatory journey as a winter intern in 2005, transitioning to a weather observer in 2006. Ryan's interests in weather started as a child when he would watch the morning weather report before going skiing. In high school, he enjoyed giving weather reports to fellow students and ski clubbers and decided to pursue a career in meteorology. He graduated from San Jose State University in 2004 with a BS in meteorology and spent the first 3 years of his career as a weather observer for San Jose International Airport. Mount Washington's unique weather and exploring and studying the worst weather in the world appealed to Ryan. When he's not watching the weather, he enjoys backpacking, ski boarding, aggressive inline skating, traveling, video games, and movies. Ryan is well known among the observatory community for his stunning photographs and why we invited him to talk to us today. Welcome, Ryan.
Thank you, Lorna, and thank you, Beth, and thank you, AMS, for allowing us the time to speak. And thank you for everybody who's tuning in to watch our presentation. So let me quickly share my screen. Hopefully everybody is able to see that. So I'm going to be talking about the photography aspect of how to capture some of the that you might see in the atmosphere. As mentioned, I work at the Mount Washington Observatory, which is located on the summit of Mount Washington, which is located in New Hampshire. Fun fact though, we're in the fog over 60% of the year, so a lot of the times I can't see very much in the way of optics, but when we do clear, occasionally we do get some really neat phenomena to capture in the skies around us. So what kind of gear might one need to capture some of the optics that you might see in the atmosphere or around the area? So the first one would be a smartphone. Everybody has on you, and the saying is your best camera is the camera you have on you. So, you know, it's a simple type of camera. It's more of a point and shoot kind of aspect, but a lot of cameras and a lot of smartphones are getting their OSs to have the built-in features of almost a full-on DSLR. So a lot of the fancy photos that you've seen with long exposures, you can almost do those on smartphones, and a lot of the software allows you to do stacked images and stuff like that. So a smartphone is a great way to get into photographing in the first place. That way you're not spending thousands of dollars on another piece of equipment and not really utilizing it like you might want to. Some other things that you might want to utilize is a tripod. They make small little type tripods that you can kind of see in the photo there, that you can kind of prop your camera up in a better angle, or if you're doing a long exposure, it allows you to kind of keep your hands off of it so you get more of a steadier shot and not getting a blur that you might get when you're moving your hand around. A lot of cameras have timers built in, so that way you can kind of take your hands off the camera and again get that more steadier shot if it's late in the day, or if you have really dark skies, it might be difficult to get those rainbow type shots, or if you're looking for the northern lights, it might be a little bit difficult to hold your camera still for 20 or 30 seconds. So both of those are more for like darker type conditions. Another thing too is to set your camera into RAW form or as high of a resolution as you can, because that'll allow you more options when you are on the back end editing your photos. And a lot of cameras also allow you to dial in a lot of your aspects now. So if you don't want to do the point and shoot aspect, you can dial it in and treat it more or less like a real camera. Once you are satisfied with what the smartphone is producing and you want to move up, another option would be a DSLR or mirrorless type camera. These are more of those interchangeable lens types cameras, which will allow you to do longer exposures, change out the lenses so you can get zoom functions or wide angle functions that point and shoots might not necessarily have, and just allows you to kind of hone in on what you're trying to photograph. Again, you might want to consider a tripod to keep your camera still during those longer exposures when it's darker out. and you might not have a lot of light. Luckily, a lot of the atmospheric optics that were mentioned earlier in the two previous presentations are occurring during the daytime hours. So a lot of times a tripod won't be completely necessary, but as you get later and later, you might have to utilize that. So one thing to kind of consider is you want to make sure that you're not using too much of your ISO, because that can either overbleed your photo or underexpose it, and that can be difficult to post-process and dialing up your image at a later point. So kind of playing around with your camera beforehand to kind of figure out what your best ISO are in different conditions will help you dial in what you need. Exposure times will vary depending on what you're trying to photograph. So if you're trying to do something during the daytime, you're going to have a much shorter exposure time than what you would have during the nighttime, where you're going to be doing, 20 or 30-second exposures to try and draw out as much light as you can during those darker situations. And then with your aperture, or how wide you're letting the light in, basically, the wider your aperture is at night, the more light you're going to be allowing in. And during the day, you're going to want to dial that down and let a little bit less light in. So that way you're getting more of a depth of field and more things in focus. So that way you're capturing more of the scene around you. So like I was mentioning, practice, 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 and learning your camera. So knowing where your ISO might be, knowing where you might be looking, knowing how to dial in those things, especially as you get into the nighttime aspect of it, because you really want to know what you're going to be setting your camera to beforehand rather than trying to figure out on the fly. Because if you've only seen the Northern Lights once in your life, you don't want to be learning how to do night photography and then also photographing the aurora. So practicing as much as you can during the daytime and at nighttime will help you dial in those rare events, so that way you know how to get what you need at the right time in the right situations. Know where you're looking. As Beth and Lourdes were mentioning, sometimes some of the features are occurring behind you, so you don't always want to look directly at the sun or away from the sun. Sometimes you can have different atmospheric effects that are occurring all around you, and you kind of want to keep an eye all around you to kind of see how the light might be playing or interacting with different elements that might be in your environment, and seeing how that's going to maybe create a better photo than what you originally envisioned. Night, you want to keep your eyes dilated. So, set your phone on night mode so that way it's a darker screen. Try and use red light so that way you're not affecting the amount of light that you're able to see. And as was mentioned, don't look at the sun. Just don't. It's not good for your eyes. So most commonly sunrises and sunsets. I usually go out an hour before sunrise or sunset and an hour after sunrise or sunset, because you have what's called the golden hour and then the blue hour. And depending on how long you're out there, you can get different tones. So the three photos that you see here are a photo I took from Mount Pierce, which kind of shows that golden sunset and then blue hour and how the different light interacts with the atmosphere and your landscape that you might be looking at. You want to look at a wide angle to get as much of the landscape you have, but you might want to zoom in and get something a little bit more in focus. It just kind of varies on what you're trying to capture. The wider angle will provide a lot more to look at, but you might have something that you want to use a zoom for. So it kind of varies. There isn't a right or wrong answer. It's kind of user choice. Halo sundogs and pillars, as Lourdes and Beth were pointing out, these typically form during high cirrus events. So typically before a warm front is moving in, the saying is, if you see a ring around the sun or moon, rain or snow will follow soon. So if you have a warm front moving in, or you're going to be getting precip in the next 24 to 36 hours, that's when it is a good time to start looking for those atmospheric optics. And they can occur most commonly with the sun, but they can also occur with the night when you have the moon at a bright enough optic. And so the left photo shows what a lunar halo looks like, and the right shows what a solar halo looks like. So time of day and weather all depends on what's coming to your area, and then also kind of keeping an eye on how much light you have available that might be forming them. Typically, you want to use a wide angle lens because these things are fairly wide, and you want to make sure you're capturing as much atmospheric effects that are occurring at one time. However, if all you have is a zoom lens, you can take a series of photos and stitch those together at a later time. Or if all else fails, you can zoom in on certain aspects of the halo and kind of get at least a partial halo in your photo, so that way you can remember the moment that you witness these type of things. Coronas typically form with more lower type clouds, and so you'll see a rainbow type effect closer to the light source, so either the sun or the moon. This is the moon in this case. And so you don't need to go nearly as wide. So something in the 24 to 50 millimeter range will usually capture what these are. And if it's at night, you're going to have to long exposure, but during the day, you'll be able to capture those with a quick snap. So they're not too hard to spot, but you do have to kind of look at the light source. And if it's the sun, that's not a great thing. So as Beth was mentioning, you kind of want to obscure the center so that way you're not getting direct effects of looking at the sun and trying to spot these. So if you put your thumb up over the sun, you'll be able to spot these a little bit easier. And then when you're looking through your camera, make sure if you're using a mirrored camera that you're not looking through the viewfinder, because that can sometimes magnify the light and cause optical damage in your eyes. So make sure you're using live view if you're going to be using a mirrored DSLR type camera. Rainbows and moonbows, again, you're going to want to go, as Beth was mentioning, towards sunrises and sunsets because the sun angle will be low enough to allow you to see the rainbows that are forming. Wide angle is typically better if you want to get the entirety of the rainbow, but if all you have is a zoom type camera, you can use that to kind of zoom in and get color on something that might be in the background or in the foreground and kind of get some neat little aspects of that. But it just kind of varies. And you can also get them at night. So if the full moon is occurring, you can sometimes get a lunar rainbow or moonbow, basically. And those can sometimes have similar coloration depending on how bright the moon is shining at your location. Fog bows are another thing. If you're in the fog, you can sometimes get what are called white rainbows. These are typically, again, when the moon or sun's low enough, they allow for the particles or the mist of the fog to basically refract the light, but it doesn't have enough time to refract into full colors usually, and so it kind of cancels itself out and gets more of a white rainbow. But occasionally, as you can see in the two images that I presented here, these are lunar fog bows, and so the droplet sizes were large enough to allow some of that refraction to allow for some of the colors in the fog bows. Light pillars are another one that can occur during the winter time. So as you have really cold conditions, you can have plates that allow the light to be reflected from neighboring light sources. And so if you have a lot of light sources, you can get several pillars in the air. These typically you need a larger wide angle lens to kind of get, the grandeur of them because they do shoot up pretty far up into the sky. And so, and typically they occur at night. You can get them during the daytime hours, but typically nighttime is when you're going to be doing. So you're going to have to use a tripod and a long exposure to kind of draw them out, but they are visible to the naked eye. So you'll be able to see them before you photograph them and then kind of frame up your shot before you, take your image. And then lastly are the northern lights. For our latitude, they're not too common, but you don't have to be on a mountaintop to see them. I've seen them down in the valley more than I've seen them up on the summit here. But as Lourdes was saying, the summit does provide a neat perspective, and you're going to need to do a long exposure, typically, somewhere in the 20-second range, but it's going to vary depending on what your equipment is. And they can occur at any point of the night. So there isn't any prime time, but typically around the middle of the night, and that varies depending on the time of year. So best thing to do is download an app that will notify you if there's a possibility of seeing them in your area, and that will allow you a chance to possibly see the northern lights in your area. And I could go deeper into that, but that's a whole different presentation. So I thank you for your time, and if anybody has any questions with the time remains, we'll hopefully be able to answer.
Thank you, Ryan, and thank you, Beth. It does not look like we have received questions. We're only a minute from the end, but maybe I want to pose one question to both of you. Have you had an experience where you saw something amazing that you're still decades or years later thinking about it?
Yes. In 2004, I saw the aurora over my neighbor's house, and I waited another 20 years for us to be able to see them again because I live at 40 North. I'm not supposed to be able to see aurora, but there was a solar storm, and so that was really amazing. And so that really was a cool thing.
And you, Ryan, do you have one?
Yeah, similar. May 2024 was the strongest northern lights I've ever seen. You could literally look in any direction up in New Hampshire here and see them. shimmering in the sky, and you could see them while you were driving. And it was just unforgettable.
And
I have-
mine, no, go ahead. I have similarly the same experience with the auroras, but one awesome experience I had was seeing a really, really rare halo effect from a plane for only a couple of seconds. And I actually put the story in my Halos Maestro article if anybody wants to check it out. But we are out of time. And thank you so much for sharing your experiences and your expertise and your wonder about looking at the sky. There's Gideon. So thank you, everybody, for your attention.
Well, yes, Dr. Vias, Beth, and Ryan, thank you so much for everything. That was very much appreciated. And yes, the icing on the cake of our Jamposium 2-day experience. And with that, folks, we conclude Jamposium 2025. A huge, huge thank you to all of our speakers, moderators, and attendees for making this yet another engaging and insightful weatherband event. We've explored everything from severe weather safety to the mysteries of the sky, and we hope you are walking away with some new knowledge, inspiration, and connections. All Jamposium sessions will be available soon for replay at amsweatherband.org, so keep an eye out. And the discussion doesn't necessarily have to end there. AMS members can continue the conversation on the AMS community forum. So if you have further things you'd like to discuss about any of the sessions and the topics that we covered these past few days, feel free to bring it up there, and we look forward to discussing it. Again, thank you for being a part of this year's Jamposium. Stay curious, stay engaged, and we can't wait to see you at future AMS events. Thank you, everybody. Have a great rest of your day and a wonderful weekend. Bye.